Welcome to the class, and today we are going to discuss more about Drude's law, Drude's model. We already discussed about it a little bit in the last class, where we discussed about why the Drude model was necessary and what kind of research gaps or science gaps did it fill. And so today we are going to extend the discussions towards the electric properties of materials which have been explained by Drude's law or Drude's model. It's not a law, but it's more like a model which has certain assumptions over what how the system behaves, and it also has a certain equations and certain phenomenological, or maybe the let's not go into the jargon, but it's basically um, a model with certain assumptions and certain laws of motion, which are obviously are also assumptions. And based on these equations, we can predict the various properties of these systems, and we will see that whether they actually match with experiment or what is seen. So let us start. So first, what we will do is we will see that what's Drude's model. So as we talked about last time, that Drude model. So this is a model where let's say there is a conductor, and how what we will consider is the electrons will be considered as free particles, or it will be called electron gas. It is called an electron gas. Why? Because we are assuming that the electrons are, they don't interact with each other, and they don't interact with each other in sense that they don't exert electrostatic force, they don't repel each other because they are so far away. So that's why we are thinking that it's like an ideal gas. So we are modeling this electrons inside the metal or the conductor as an ideal gas. And what are the conditions of ideal gas? The particles of ideal gas, the particles in this case, which will be electrons, do not interact with each other. With each other. So that will be the uh, like primary assumption, that the electrons don't interact with each other, the electrons don't collide with each other. So interaction does not mean collision, or it does not even mean the electrostatic interaction. But in this case, what we can sometimes what is done in ideal gas, that ideal gas, the gas molecules can actually collide with the box or the container that they are in. So what we can say is that the electrons will rarely collide with the positive nuclei or the ion centers. So there are ions and there are nuclei, right? So sorry, there are nuclei and or ions, then there are electrons. So let me draw the ions with a different color. um, so let's say there is an ion here, there is an ion here, there is an ion here. In general, we will be talking about crystalline substances, but we can also talk about in general any conductor. This model does not have any crystalline substance, it doesn't need to be, it's valid everywhere. It, yeah, not necessarily only in crystalline substances. So what the electron does is, the electrons are free, they don't interact with each other, but they can interact with the ion centers. So they can go and they can collide, they can collide, they can collide, they can collide, they can do this. So it's basically like a Brownian motion, right? um okay. So yeah, so let's say there are this ion center, ion center, ion center. Now there is an electron which goes like this, and after time tau it collides again, then after time tau it collides again, and so on. So sometimes the tau is called the characteristic time of collision. It's not called this, but it's the characteristic time of collision, right? um, that is one thing. Then the other thing would be that the electron is an ideal gas. Electrons are constituting an ideal gas, so they are thought to obey Maxwell-Boltzmann distribution. They are following the Maxwell-Boltzmann distribution. And what's the Maxwell-Boltzmann distribution? It gives us the probability of how are the velocities of the particles or the gas molecules in an ideal gas looking like. So we don't go into very much detail, but it's of the form f of v is some constant k, v to the power minus 2, 1 by v square. V square, not v to the power minus 2, rather v square, e to the power minus beta v square. So this is like the probability distribution. If we plot it, it looks like this. So this is the probability distribution of, so this, let's say this is the number of count or probability, and this is the velocity. So this is how it looks like. So for every velocity, you will have a certain probability of the particles to be in this velocity, right? So this is called the most probable velocity, because I mean the probability of a particle being in this velocity is the highest. We can also define the mean velocity. We can also define the square root or RMS velocity in different things from this distribution. Generally, we talk about the RMS speed because it gives us what is RMS speed. So V RMS whole square will be V1 square plus V2 square dot Vn square divided by n, where number is the total number of electrons, total number of electrons or gas molecules. Okay, so from this we can actually get that for a gas which is at temperature T, this is the RMS velocity, uh, where let's say this is the ME, or mass of an electron. Mass of an electron, Kb, is a Boltzmann constant. Okay, so that's what we will get from this. So that is a digression, and that is a little bit of digression, but it's very important to understand that how the electrons are being modeled, to better understand the concept of how we are going to define, because the VRMS is taken to be the standard velocity. It's the energy of a system where every particle has a velocity of VRMS, and the energy of a system which has particles in the Maxwell-Boltzmann distribution will exactly be the same. Okay. So now what the thing is, how does it uh, okay, so let me draw another conductor. So now what we are saying is we apply an electric field, right? So what happens is, let's say there is a positive ion, 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 so there are a lot of positive ions, right? And then electron was coming like this. Okay, then it went like this, then it went like this, then it went like this. Okay, but now what will happen is, because of an electric field, when it goes, then it will be slightly displaced because due to the electric field. Okay, so I think I drew the direction wrong. Yeah, so let's say this is the electric field. Yeah, so the force on the electron will be towards the right side, right? And due to the electric field, the electron will start drifting. So as we can see that slowly, the yellow path and the blue path will start diverging. And uh, so basically what we are seeing is there is a drift. This is called the drift velocity. Okay, so how to understand this concept of drift velocity? We are saying, so there are two concepts which are very important to be said. That is, there might be questions in people's mind that, okay, we are assuming that the electrons are following a Maxwell-Boltzmann distribution, but again, due to electric field, the velocity of each electron is increasing. So, is the electron gas actually following Maxwell-Boltzmann distribution after some time? Because there has been a change in the velocities, right? Because of the electric field. The answer is that no. The electron, if indefinitely it is being accelerated by an electric field, eventually it's not going to follow Maxwell-Boltzmann distribution. But what we are assuming is it's colliding with the positive ions and it's losing this extra acceleration. And the thermal equilibrium or the Maxwell-Boltzmann distribution is regained back. So to understand this concept, you can say that okay, there was an electron, there was an electron, there was an electron, there was an electron. They were following Maxwell-Boltzmann distribution. But after some time, due to the acceleration due to the electric field, everyone has got a slight bit of drift velocity. So the energy is not conserved now, and also the um, energy is not conserved, and the electrons are not really following the Maxwell-Boltzmann distribution. The distribution has been changed. But what we are saying is this extra drift velocity is being lost when the electrons are actually colliding with the positive centers. So when it collides with the positive centers, then we will consider that the collisions are a little bit inelastic in such a way that when it collides, after that it comes back, the electrons come back after collision and they regain this Maxwell-Boltzmann distribution. They have lost this extra drift that they got, and we will assume that the collisions are pretty frequent. So more or less, if we see from outside, the Maxwell-Boltzmann distribution will be pretty much safe. So we can go ahead and approximate that the gas is always in MB or Maxwell-Boltzmann distribution. So that is a core assumption that we are going to take. Okay, right. So now that being done, what we are saying is, let's say there are two positive centers, right? And the average velocity of an electron from this to this will be what? Vrms, which is given as 3 kbt by me, right? Okay, so now what we are going to see is that if the total time is tau, then L, or the mean free path, this is called the mean free path. So L will be given as Vrms into tau. Okay, now let's say that the electric field was turned on here. So the electron actually went like this. So there will be an extra velocity delta V that is given as what? That is given as tau into E by me. So this is the acceleration, this is the time. Okay. So this is called the drift velocity. So tau E me. So this is the drift velocity that the electron actually acquired. This analysis is a very simplified and oversimplified analysis. So this is often called the drift velocity. Drift velocity. This is a very important formula and this is actually the core. This is the base formula for Drude's model. Okay. Okay, so this is what we can kind of get, and this has also to do with a lot of probability distributions. This is an oversimplified version of the analysis that I am showing you. So we can see that Vd is equal to mu into E, when mu is given as tau into E by me. Okay. Yeah. So this is basically saying that the drift velocity will be directly proportional to the electricity, the electric field. Now what we can do is we can see that how the conductivity, resistivity, these things can be now I mean these can be calculated. So we can see that, let's say this is a conductor, a cross section of a conductor with area A and length L, and electrons are going inside it with what velocity? With drift velocity. Drift velocity, by the way, is far lesser than the RMS velocity. RMS velocity is very fast, but it's random. So for every electron going forward, there will be an electron going backward. But with drift velocity, what we will see, the electron going forward will go a tad bit more forward, and the electron going back will go a tad bit less backward. So in effect, there will be a drift. In effect, the electron mass will move forward, even though some electrons in the mass are moving backward, but the mass as a whole, the electron gas, is moving forward by a very small speed. So that is what is called the drift. That's why it's drift. Okay, so now the drift velocity is there, and then let's say the electron density is n. So we can say that the how many number of electrons are actually passing per unit time. So per unit time, so dn dt is what? N into Vd into A. So it's a simple geometry. So it's basically the number of electrons which are contained in the volume that has been passed through this area. This is area 1. So this volume of the electrons is Vd into A, and the electron density is N. So the number of electrons passed in this time frame is dn dt, is nvd into A. So what is the charge that passed? So that is also defined as current. So Ne into Vd into A, because we multiply the number into the electronic charge. So we got I equals to Ne Vd A. Okay, now we can put the Vd, which is mu into E, or we can also put it as tau into E in by Me, right? So we can get n e square A by Me into E. Okay, now the I by A, this term is often called current density. This term is often called current density. So this is for a simplified analysis. In general, A and J are vector quantities. We will see why. But in that case, what we get is J equals to Ne square uh, tau by Me into E, which is also called sigma into E. So the sigma is called the conductivity, which is given as Ne square tau by Me. Okay, so these are the main relations that we get. Mu d is E tau by Me, and sigma conductivity is Ne square tau by Me. And this J equals to sigma E is often called Ohm's law. And if we write E to be V by D, or the potential difference divided by the distance, then we can actually recover V equals to IR, which is the Ohm's law, which is the Ohm's law that is fairly known to every person. Um, this is the Ohm's law that we are talking about. In like we see it everywhere, where this R is often written as L by sigma A. Okay, so I mean we this was the magnificent or the genius of Drude's model, which actually gave us the Ohm's law, which actually helped us derive the Ohm's law, and it also gave us these fundamental quantities about the intrinsic or fundamental quantities about materials, right? So this is the genius of Drude model, and yeah, so this is the recap of what we did. We said that the Drude model is basically considering electron as a classical gas, or which is an ideal gas which is following Maxwell-Boltzmann distribution, and from that we discovered that how applying an electric field will make it drift, and how the collisions with the positive ion centers will help us retain the Maxwell-Boltzmann distribution. And from the drift velocity we calculate the mobility, which is also called the mu. This mu is called mobility, which is an intrinsic property. And again, the sigma or the conductivity, which is also an intrinsic property. And we also ended up deriving the Ohm's law, and we also related resistance with conductivity. So in the next class we are going to see how the Drude's model predicts the thermal transport. So we saw the transport of electricity. Now we will see how the Drude model marries the concept of electricity and thermodynamics or the thermal transport, and how we will get some reunification of the transport of electricity and heat. So see you in the next class. Thank you.